Hi, in this video, I'm going to explain how we can write a program in Octave for numerically solving a first order ordinary differential equation using the Runge-Kutta method. The program which we are going to write can be used with Octave or MATLAB or any other MATLAB clone. You can use the program as such or with minor modifications required by the concerned software. Before writing the program, let us see some theoretical background and an example differential equation for which we are going to write the program. Let us consider a function y of x described by this curve. Y of x is a function of x. If this y of x is differentiated once, you will get a first order differential equation. The first order differential equation will be of the form dy by dx is equal to f of x comma y. That is, this also is going to be a function of x and y. We represent that function as f of x comma y. Solving a differential equation means getting back this y of x from this first order differential equation. In any practical system, we can write the differential equation describing the systems easily, and therefore it is necessary to get the solution to understand its behavior. Therefore, solution of differential equation is useful in many studies. One can get the solution of the differential equation in two ways, namely analytically or numerically. In analytical solution, we get a closed form of the solution as a function of the independent variable, and thereby we can find y of x for any value of x for which y of x exists. But in numerical methods, we start from a known initial value and find the discrete points x1, y1, x2, y2, x3, y3, and so on. So we start from a known initial value. We call that initial value as x0, y0. Usually, this x0, x1, x2, x3 up to n are taken at equal intervals. We call this interval as step size, and usually it is denoted by the letter h. The smaller value you take for h, the better accuracy you will get in the solution. Anyhow, to find out the solution of this differential equation, the initial value has to be known. So let us say that initial value is x0, y0 as said before. And from this initial value, we need to find the next point, that is x1, y1. And then from x1, y1, we should find x2, y2. Clearly, x1, x2, x3, and so on up to xn can be easily found if we have taken a fixed interval h, because if the fixed interval is h, then x1 is going to be x0 plus h, and similarly x2 is going to be x1 plus h, and x3 is going to be x2 plus h, and so on. And the corresponding y values are y of x0, y of x1, y of x2, y of x3, and so on up to y of xn. Since x1 is equal to x0 plus h, then y of x1 is equal to y of x0 plus h. Therefore, if we have some formula to find out this y of x0 plus h, we can find out y1. Therefore, if x1 and y1 are known, then from x1, y1, we can find x2, y2 in the same way as we found x1, y1 from x0, y0. Similarly, we can move from one point to all the successive points, and we can get all the points on the curve, and then we can get thereby we can get the solution of the differential equation. There are a few numerical methods which give direct formulas to find these successive points on the curve. And these methods we call as explicit methods of integration. One such method is Euler's method, and this method is explained in another video. Runge-Kutta method is also another explicit method which we will be seeing in this video. Both Euler's method and the Runge-Kutta method are based on the Taylor series, and both are the explicit methods, and depending upon the number of terms considered in the Taylor series, the order of the method varies. For example, Euler's method is a first order method, whereas in Runge-Kutta method we have got second order, third order and fourth order methods. In this video, we will be taking up only the fourth order method, and if one is confident of writing a program for the fourth order Runge-Kutta method, definitely he or she can write the program for second order or third order method also. So here is the direct formula to move from x0, y0 to x1, y1, that is x1 is x0 plus h and y1 is y of x0 plus h. And we have got a direct formula to move from x0, y0 to x1, y1. So this is the formula. Y of x0 plus h is equal to y of x0. Y of x0 is nothing but y0 plus 1 by 6 into f1 plus 2f2 plus 2f3 plus f4, where the functions f1, f2, f3 and f4 are defined as shown here. We'll take up an example and we'll understand how we can calculate this f1, f2, f3, f3 and f4 and thereby the points on the curve and get the complete solution. So this is the example what we have taken. So the differential equation we have taken is dy by dx is equal to y into ln y by x. And we need to find out the solution starting from x is equal to 2 up to x is equal to 3. So as I have already told you, for solving any differential equation numerically, you need an initial value. The initial value given is y of 2 equal to e. That means y of x naught is equal to e. That means x naught is equal to 2 and y naught is equal to 3. So we will proceed with the steps for solving this equation. Given the initial values are x naught is equal to 2 and y naught is equal to e. And dy by dx is equal to y ln y by x, that we take it as a function f and it is a function of x comma y. Therefore, wherever f of xy comes, it means that it is the expression for dy by dx. dy by dx is the differential equation, and whatever is given for that differential term, we take it as f of x comma y. As I said previously, the h has to be chosen to be very, very small, lesser than 1. And I have taken a h value of 0.01. So let us find f1, f2, f3, f4 and then y1, that is y of x naught plus h. f1, the formula for f1 is h into f of x naught, y naught. That means the value of h multiplied by the function f evaluated at x naught, y naught. So take that function, Substitute x is equal to x naught and y is equal to y naught. You get f of x naught, y naught. So if you substitute all these values, because we have the initial values already, and h also we have taken as 0.01, we can substitute those values and this is what we will be getting. We got the value of f1. Now it's a time to get f2. Formula to calculate f2 is h into f of x naught plus h by 2 comma y naught plus f1 by 2. So the function f has to be calculated at some other point. The points are x naught plus h by 2 and y naught plus f1 by 2. So therefore, to calculate f2, we need f of x comma y evaluated at this coordinate. So let me call these coordinates as x naught 1 and y naught 1. So x naught 1 is equal to x naught plus h by 2 and y naught 1 is equal to y naught plus f by 2. Since x naught, h and y1 are already available with us, we can substitute those values here and we can find out the coordinates. Now f2 is defined as h into f of x naught 1 comma y naught 1. X naught 1 is equal to this and y naught 1 is equal to this, and that coordinate we have already found. So f of x naught 1, y naught 1 is equal to h into f of x, in which x is substituted with x naught 1 and y is substituted with y naught 1. Since h, y naught 1, x naught 1 are already known to us, we can substitute those values and this is what is the value we will get. We got f1 and f2. The same way we need to find out f3 and f4. f3 is calculated in the same way as we calculated f2. The only difference is the y coordinate is not y. Previously it was y naught plus f1 by 2. Now it is f2 by 2. In the same way we calculated f2, we can calculate f3. The new coordinates, let us call it as x naught 1 and x naught 2. So we can calculate them as we did before. And f3 is equal to h into f of x02 comma y02, and you can substitute those values and this is what you will be getting as the answer. So we got f1, f2, f3, and the fourth step is to find out f4. f4 has to be calculated at these coordinates, x0 plus h and y0 plus 3. So let me call it as x03 as x0 plus h and y03 as y0 plus f3. So since those values are available to us, you can calculate and this is what you will get. And when you get these coordinates, we can calculate f4 also. f4 is obtained by h into f of x03 comma y03, and this is what you'll get and this is what is the value. Once we get the values for the functions f1, f2, f3 and f4, we can find the new coordinates. So that means we are moving from x0, y0 to x1, y1. x0 is equal to x0 plus h, x0 is 2 and h is equal to 0.01. That's equal to 2.01. And y1 is equal to y of x0 plus h, y of x0 plus h by the Runge-Kutta formula. This is what is the formula, and y0 is equal to e. We had already calculated the values of f1, f2, f3, f4. Just substitute those values and we will get this as 2.7319. So the new point is x1 comma y1 is 2.01 comma 2.7319. Now we have found x1 y1 from x0 y0. Now it is the time to calculate x2 y2 from x1 y1. What you need to do is just take x1, y1 as the initial values and proceed in the same way as we did in steps 1 to 5. You will be getting x2, y2. The new point will be 2.02, 2.7456, and proceed in the same way. Take x2, y2 as the initial values and find the new coordinates x3, y3, repeating these steps 1 to 5. Anyhow, the steps 1 to 5 have to be repeated until you reach xn is equal to 3, until you reach xn, which is given as 3. So we are finding the solution from x is equal to 2 to x is equal to 3. So, having understood how this Runge-Kutta method is used for the solution of first order differential equation using with the help of an example, let us make this process into a program. We'll use the Octave software. This is the GNU Octave software, and we'll open a new script file, new script. It will start a new script file in the editor, and here is the command window, and here is the editor window. The editor window and command window can be toggled between. We'll start typing the program. You know, any program has to be commented well, and any comment is started with a percentage symbol. So we'll start the commenting. It's a Runge-Kutta method for solving any first order differential equation. We are going to find out the solution of a differential equation given as y dash of x, that is dy by dx, is equal to y into ln of y divided by x, with the initial conditions x naught is equal to 2 and y naught is equal to e. We need to simulate from x is equal to 2 to x is equal to 3. For any program, the first statement should be clear all, that is to clear all the variables which are assigned previously, which are defined previously from the memory. And it is better to clear the command window also. So the command used is CLC. Now you have to give the inputs. The various inputs for this numerical algorithm are the initial values, the step size, and the final value. The initial value is x naught is equal to 2. This is the starting value for x, and y naught is equal to e. So we are given the initial values. Now let us define what is the final value. The final value, we are taking it as 3. So x, this is the final value at which the simulation or the solution has to stop. Now the step size, we are taking it as 0.01. You can take any step size. Almost all the inputs we have given. Now the computation has to start. We start the computation. In the computation, the first thing to do is we need to find out x1, y1 from x0, y0. So you need to calculate f1. That is what is to be calculated first. f1 is nothing but h into f of x0, y0. f of x0, y0 is the function given here, with x substituted with x0 and y substituted with y0. So that function is written here. Please note that for the natural logarithm in Octave and MATLAB, the function is log. For log to the base 10, the function is log 10. So since it is the natural logarithm here, we are using the function log of y naught. So f1 is calculated. To find out f2, we need x naught 1 and y naught 1. They are calculated. X naught 1 is equal to x naught plus h by 2 and y naught 1 is equal to y naught plus f1 by 2. Once that is calculated, we need to calculate f2. f2 is nothing but h into f of x naught 1, y naught 1. Again, it is the function where you substitute x with x naught 1 and y with y naught 1. In the same way, you need to calculate f3. To calculate f3, you need the coordinates x02 and y02. x02 is same as x01, that is x naught plus h by 2, and y02 is equal to y naught plus f2 by 2. Once it is calculated, you can calculate the f3. It's same formula as f2. Only thing is you have to use the new coordinates x02 and y02. Now is the time to calculate f4. To calculate f4, you need x03 and y03. x03 is equal to x naught plus h and y03 is equal to y naught plus f3. So f4 is calculated. f4 is here, h into f of x03, y of x03. So once that is calculated, f4 is done. Once f1, f2, f3 and f4 are calculated, you can find out the new coordinates. x1 is equal to x naught plus h and y1 is equal to y naught plus 1 by 6 into f1 plus 2f2 plus 2f3 plus f4. All the values are available to you. Just write the expression. Octave will calculate it for you. So we have got the new point x1, y1. Now, taking x1 and y1 as the initial values, that is, you assign x1, y1 to x0, y0 as x0, y0 and repeat the steps 1 to 5. Otherwise, repeat these f1 to f4 and x1, y1 steps again. So here we are assigning the x1, y1 values to x0, y0 and we have just copied the same steps again. So with that, you will get x2, y2. Let us run this program. So we will press the run button. And we need to save the file before running. So it is run. So let us, in the command window, let us type x1, y1, x2, y2. So we got these values and we can verify that these are exactly the same values what we got by our computation. So the program is correct. But here we see that this particular set of steps are being repeated again and again. So therefore, we can put these steps in a for loop. The steps 1 to 5 are getting repeated, and therefore instead of writing the steps again and again, I can put it in the for loop. For the for loop, the variable is x. X varies from x0 to x final with an interval of h, and the for loop has to be entered. And in the for loop, when you execute the for loop, every time that values have to be stored. So therefore you need a counter, and we take the counter k is equal to 1. I initiate the counter k is equal to 1, and every time the program moves into the for loop, the counter has to be incremented. So that is why we put k is equal to k plus 1, and at the same time So this the whatever value we calculate have to be stored. The first value to be stored for x and y, or the initial values, they are stored. The initial values are the first value in the array. So all the values of x and y are stored in the arrays uppercase x and uppercase y. So instead of 1, I can use the k value also, because before entering the loop, the k value is 1. So when this loop is executed for the first time, when it enters the for loop, the k value will become k plus 1, that is, k value will become 2. So at the end of execution of all these steps, you will be calculating x1, y1, that has to be stored in x2, x of 2 and y of 2. So you can use this index k for storing it as capital X of k and capital Y of k. And for the calculation of this functions f1, f2, f3 and f4, you need these initial values. For the first time when this program enters the for loop, the initial value should be x0 and y0. When the program enters this for loop for the second time, the k value will be 2, whereas for calculating this f1, f2, f3 and f4, we need the values x1 and x1 and y1. So therefore, all this x0 have to be replaced by uppercase x of k minus 1, and all the y0 has to be replaced by y of k minus 1, uppercase y of k minus 1. So that is what we are doing. Please note the k value for when the program enters this loop, for it enters for the first time, the k value will be 2, and the value calculated, x value calculated and y value calculated, has to be used in they have to be stored in k, x of k, capital X of k and capital Y of k. So the x0 and y0 are replaced by k minus 1. Once we complete all the addition inside the loop, it is time to plot the curve, plot x comma y. So we need to plot, and let us say executing. So there is an error, we will correct it. Yeah, there is one bracket missing. There is the brackets are not balanced, so we have done it, and now we can, yeah, everything is right. So now you can run it. Yeah, we got the solution. Okay, so we have chosen the final value as 3. You can change the final value as 10, and you can run the program. Yeah, you got the solution. That's great. So with an initial value of x is equal to 2 up to x is equal to 10. However, there is a scope for improving this program. The reason is, in the example what we took, the function happened to be a very simple function, but it need not be so. It can be a complicated function. So the function value has to be calculated at 4 places. When f1 is calculated, for f2, for f3 and for f4, the function has to be calculated. So rather than writing the functions again and again, you can use the function in Octave program to calculate the function values. So that is what we will do. We will create a function, and we will use the value evaluated by the function to calculate the f1, f2, f3 and f4. The function can be written anywhere. We need to write the function anywhere before the function is called in the program. The function part starts with the command function and it ends with end. So this is a function to evaluate y dash, or y dash is equal to f of x comma y. Since we have already used the variables x and y in the program, I'm using the variables a and b in this function. So function start with function and end with end. And whatever result, whatever is calculated using the function is stored in the variable called result. As I said, instead of x comma y, I'm using a comma b. The result is the function calculated, it is y log y by x. So we are using a and b. So instead of x comma y, I'm using a comma b. So now I can just call the function by f. The function name I have given as f. F of, only thing is I need to give the coordinates here. So whenever this is executed, it will go to the function and calculate that function value at x02 and y02. In the same way, all the function evaluations were replaced. Fine. Now let us save and run the program. Yeah, we got the solution. Fine. From x is equal to 2 to x is equal to 10. Well, we understood how the Runge-Kutta method can be used for solving a first order differential equation, and also we implemented that in an octave program. As I said previously, the same program can be used with Octave or MATLAB or any other MATLAB clone. You can use as such or with minor modifications as required by the chosen software. Thank you.